Okay, I've got video for this one, so hopefully this will be a little easier to follow than the voice only recording. I want to pick up where I left off yesterday and continue our discussion on the general linear model. And this time we're going to move on with analysis of variance. We are continuing to work through the lecture, the linear model lecture, so lecture 10, the general linear model, on slide 52. I think if I've got this set up right, you should be able to, the recording should be picking up the screen that I am sharing with you, which is slide 52, but just follow along, that's where we're at. We wrapped up our discussion of linear regression yesterday, and we hinted at the analysis of variance. And if you recall, some of the diagnostics, part of the how we judge whether we have a good model in regression, makes use of the analysis of variance. I mentioned that the two are, when we started, I said the two are really the same thing, and they are. It's exactly the same model. It's exactly the same process. The math is all the same. The only thing that's different is what you're trying to do with it, what the goal is. For a linear regression, we're generally trying to build a model to use predictors to predict a response. So we're after a predictive model. For analysis of variance, we're less interested in a predictive model, and we're more interested in determining what factors in the predictors drive significant change in the response. What makes a good analysis of variance model may not make a good linear regression model. So let's kind of move forward with the analysis of variance. It's more commonly called ANOVA. In the ANOVA setting, we're primarily interested in breaking down the variation for the linear model. And to go back to the linear regression model, the ANOVA table is one of the outputs that we get. We're really going to focus on how that table is built, and we're going to break the variation into a few more pieces. So analysis of variance is all about decomposing variation in our response into a bunch of pieces and figuring out which pieces are significant and which ones aren't. What we're really interested in for the ANOVA is what's called group mean differences. Previously, we were using a t-test to look for differences between two groups. So if we go back to inference for sample means, and we looked at hypothesis testing to compare two sample means, we're using a t-test. Well, that's fine when you have two groups. It's not fine. You can do it, but it becomes more cumbersome when you have more than two groups. With more than two groups, you've got more places to look. We're still interested in variation of the group means around a central tendency. That tells us on average how much each group is different from the central tendency. In other words, it's telling us if the group categorical variable is significant. All right, so we're not going to, as we see, we're not just going to do a bunch of t-tests and try and figure out, piece together which is significant. That would work, but it would be kind of a cumbersome process. The ANOVA framework gives us a little bit of a neater way to do it. So why is it called an analysis of variance? Because that's exactly what we're looking at. We're looking at variability. We're breaking down variance. We're breaking down variability into pieces. We're looking at the average mean variability around an overall grand mean. And what we want to do is we want to compare that to the variability around each group mean. All right. So in essence, if you look at the if you look at this slide, we have total variability broken down into some conceptual pieces. This is exactly what we saw when we were looking at the ANOVA table with the regression model. It's the same idea. Our total variability has two pieces to it. It's the variability between the groups, and that's what we're going to call variation between groups, or the treatment effect. And then there's random error. There's variation of each person or each item's score around their group mean. That's variation within the groups, or variation due to random error. And for analysis of variance, the basic rule of thumb, the key is if the variation between groups is big enough compared to variation within the groups, then that variation is significant. The tool that we use to look at this, similar to the regression framework, is sums of squares. Excuse me. So we're breaking variation down using sums of squares, just like we did with regression. And just as with regression, the sums of squares total is can be broken down into pieces. Now for starters, we're going to break it into two pieces: the error sum of squares and the group sum of squares. This is analogous for that regression ANOVA. We had the sum of squares due to the regression. That was our model. And then we had the error piece. Okay, so it's the same two pieces that we're really looking at. Now, depending on how many pieces go into the group sum of squares, that portion can be further decomposed, depending on what we call the experimental design. If we have multiple treatments or multiple factors that we're controlling for, multiple things that we're considering as part of our model, then that group sum of squares gets broken down into more and more pieces. When we look at multiple regression, so that's linear regression with multiple predictor variables, the model sum of squares can be broken down into sums of squares for all of those predictor variables in the same way. All right, so we can look at which predictor is significant and which is not. So that's what we're doing here. All right, so how does this work? Well, we have two sources of variation, and we're using the sums of squares and the relative sizes. So ultimately working with mean sums of squares. Variation between groups, that's SSB for sum of squares between, and you can see the formula there. Y double bar as our overall grand mean. All right, so that's all adding all of the data together and dividing by the number of data points. And Y sub j is the mean within each group. As once we get to a practical problem, this will be a little easier to understand. Sum of squares error, or sum of squares within groups, is our error sum of squares. Okay, variation within groups, SSW, or sum of squares error, SSE. There's the formula right there. For each data value, we're looking at the difference between that value and the mean of its group. Okay. Now, when the sum of squares between groups is large compared to the sum of squares within groups, then we conclude that the group variation, the treatment that we're looking at, is significant. All right, we're using the same linear, general linear model that we were using for linear regression. The general linear model it's the basis for most inferential statistics. It's a framework that incorporates linear regression, analysis of variance, and their multivariate counterparts. General form of the GLM, the general linear model, is Your response equals some overall grand mean plus your group variables. So that's your effect due to your groups plus random error. For the one-way case that we're looking at, the one-way ANOVA case that we're looking at right now, we can write this as follows. YAJ equals mu, that's your overall grand mean, plus alpha j. Alpha j is the treatment effect, and epsilon ij, those are your errors. Just like with linear regression, we have an assumption on the errors, and it's a critical assumption that the errors are independent, they're normally distributed, and their means are all zero. Okay. Now, more complicated variations of this model will break down the alpha into multiple pieces. So this is a single treatment, a single group effect. You can break that down into different pieces. We might have two grouping effects. So you'd have an alpha j and a beta k in there, say, then your error term. You can also have interactions. So you can use, in the same general linear model, we can model interactions between the different factors as well as their main effects. So all of this kind of stems from this general model here. The basic idea behind the generalized linear model is that every member of the population has the same basic score, the same grand mean, and that is then changed by effects of those treatment variables. In the one-way case, that's just the alpha, and in addition, there's some random noise involved. Some levels of the treatment might raise scores from the grand mean, other levels might lower scores from your grand mean, and others might have no effect. The error, the epsilon, is the noise caused by either other variables that you're not measuring, things that you're not aware of, or things that you're not controlling for, as well as just individual to individual variation, right? For a treatment effect to be significant, it's got to be large enough to kind of overcome this noise, large enough to stick out compared to the error noise. Okay, so let's talk a little bit more about that error term. Like the treatment, the error is going to have different effects on the scores, but these effects happen independently of the treatment effects. If the errors are too large, then it's going to mask the effects of the treatment, which means it will be impossible to analyze whether your treatment is significant or not. Most of the effort in what we call experimental design is setting up the ANOVA problem to start with. That is minimizing the error, making sure we're accounting for enough things that might contribute to that error variation so that the effect we're interested in isn't buried in the noise. Okay, the error term is important because it's giving us a yardstick, if you will, to measure the variability caused by the treatment effect. But we want to make sure the variability attributable to our treatment is greater than what's naturally occurring, greater than our error variability. But one way we can do that is make sure that we're taking things out of the error that might contribute to the variation. Maybe we're not interested in those things, but we're accounting for them. So a conceptual example, suppose I'm testing a new let's say a new diabetes medication, all right? And I'm insulin levels are what we're tracking, and that's the treatment. So the treatment effect will be to have the medication or you don't. That's what I'm interested in. That's really the primary thing that we're interested in. But if we want to make sure that we're going to, when we're looking to see is that treatment significant or not, is it having an effect or isn't it, we want to make sure that we can control for all of the other things that might that might contribute to, say, insulin levels, your age, your weight, etc. So those are all things that we want to account for, because if we leave them in the error term, so we don't account for them, then they get left in the error, and we might the effect might be working, it might be significant, but we're not necessarily going to pick it up because we just have too much noise going on. Okay. Now, one-way ANOVA. That's our simplest ANOVA setup, so that's where we're going to start. That one-way model is the Yij equals mu plus alpha j plus epsilon ij, where the epsilons are error. That's our simple one-way framework. Now, the treatment variable, it's called one-way because there's one treatment that we're interested in. But that treatment variable can have several levels to it. Okay, so you might have, for example, 4 doses of the medication, or you might have, maybe we're interested in looking at income level as a treatment, and then you could have several income levels that you break it down. Typically we're doing this as we're treating these things as as categorical or discrete treatments, treatment levels, but there are some variation. You can do continuous. We're gonna kind of hold off and look at a simpler framework for now. At the simplest, the ANOVA framework is testing the following basic hypothesis. The null hypothesis, alpha k equals alpha j for all k and j. In other words, it's saying the treatments are all the same. Okay, the alphas are all the same. The means are all the same for all levels of the treatment. In other words, the null hypothesis is the treatment has no effect. Okay, remember when we first started talking about hypothesis testing, that's kind of the rule of thumb for the null hypothesis. The null hypothesis is generally no effect. Okay, the alternative is simply that for some k and j, alpha k is not equal to alpha j. Now, the alternative isn't telling you which groups are different, just that at least one of them is. Okay, the treatment variable has a significant effect, though we're not quantifying the effect. We're not saying which groups are different, just that at least one of them is. Okay, and we're not saying we're not precisely quantifying the significance of the effect. We're just saying that it is significant. Okay, that's our simplest hypothesis test for the ANOVA framework. All right. Now, picking out significance is all about sums of squares, and it's really all about mean sums of squares. So it's all about understanding degrees of freedom. Degrees of freedom are necessary to determining the mean sums of squares, and mean sums of squares are ultimately what we're looking at. If the treatment variable alpha j has capital J levels or groups, okay, we would write this alpha j for j equals 1 to capital J. Then we're saying the treatment degrees of freedom would end up being capital J minus 1. Number of levels, or the number of groups you have, minus 1. If you have capital N data points, okay, then your total degrees of freedom are number of data values less 1. That's what we would expect. Okay, but more important than that are the error degrees of freedom. That's going to be your number of data points less your number of groups. Now, note that if you look at j plus 1 plus n minus j, you'll notice that you get n minus 1 for the total degrees of freedom. Note that just like the sums of squares, degrees of freedom are additive. The treatment degrees of freedom plus the error degrees of freedom equals the total degrees of freedom. Okay, kind of a good cross-check to make sure you got your degrees of freedom right. All of the information that we're going to derive from an ANOVA is all going to be given in the ANOVA table. This basic ANOVA table looks exactly like the one from your regression output previously, and it is the same ANOVA table. All of our calculations can be captured in this. It's going to show us our sum of squares breakdown, the degrees of freedom breakdown, the mean sum of squares, and the mean sum of squares is simply the sum of squares divided by its degrees of freedom, and the F statistic and the p-value associated with the F statistic for the particular F distribution that we're using. Okay, so you'll notice on slide, let's see, sorry, we're on slide 62 now. Okay, so let's look at an example of a one-way table. This is an analysis of variance output table. And you have your basic one-way table has 3 rows to it. You have your treatment row, your error row, and the total. Okay. You'll notice the degrees, you've got the degrees of freedom column, okay, and again you can cross-check that they're additive. Your total degrees of freedom equals your error plus your treatment degrees of freedom, and then you have your sums of squares, and I've shown here which sum of squares formula goes with which number here. Your treatment sum of squares, that's your sum of squares due to groups, all right, or SSB, that goes here, okay, that's your 34.74. The total sum of squares at the bottom, that's the 94. That is your sum over groups and observations of each individual data point minus the grand mean squared. And your sum of squares within groups, you're summing over both groups and the number of observations in each group, and you're taking each data value minus the group mean. Okay, that's the 59.26. The mean sum of squares is simply your total sum of squares divided by the degrees of freedom. The F statistic is your treatment sum of square, mean sum of squares divided by the error mean sum of squares. And that's going to be on, so we're looking at the 17.37 divided by 2.69. That gives you 6.45. That's an F distribution on 2 for the treatment degrees of freedom and numerator degrees of freedom, and 22 for the error, which is the denominator degrees of freedom. This is the p-value, 0.006, that goes with that. All right, so next slide, determining significance for the F values. All right, this is what I just talked about. All right, so mean sum of squares for groups is your sum of squares between groups. That's 34.74 divided by 2 degrees of freedom. Mean sum of squares due to error is your error sum of squares divided by degrees of freedom. The F statistic is the treatment mean sum of squares divided by the error mean sum of squares. Because again, what we're really asking ourselves is the variation between the groups or due to the treatment large enough compared to the error variation. And the p-value comes from the F statistic on your group degrees of freedom and error degrees of freedom. Now, since your F value is your mean square between divided by the mean square within, a large value of F is going to tell you you have relatively more differences between groups than within groups. And we interpret this as evidence against the null hypothesis. The null hypothesis, recall, is that the treatment has no effect. So if you have relatively more differences between groups than within groups, that's evidence against the null hypothesis. That's telling you your treatment might have some effect. To get the p-value, we just look at the F distribution on the number of groups minus 1 and the n minus j, that's the number of data values minus the number of groups, and that's our F distribution. Okay, now let's talk about some common experimental designs for a one-way ANOVA. Okay, so the one-way ANOVA, one factor completely randomized design is our basic one-way ANOVA. Okay, that's what that's called. Total sum of squares is treatment sum of squares plus error sum of squares. But we can generalize that to include multiple treatments and multiple control options. Okay, for example, we have something called randomized block designs. Okay, a block is a factor other than the treatment that might affect the response. Now, in the one-way case, we're leaving that effect. We're not parsing it out separately, but we're leaving it in the error term. But if that's significant, if that's a factor that is significantly driving variation, and we're not accounting for it, then it might make the error sum of squares relatively large, and we're not going to see the significance of the treatment because of that. So what block designs do is they allow you to parse out these other factors that we say, okay, we know these are important. We know these drive significant variation, and we want to account for them, even though that's not what we're interested in. What we're really interested in is the treatment. But we're accounting for the block factors because we want to make sure that we're, again, everything that you can pull away from the error sum of squares is going to make it more and more likely you're going to see a significant effect due to your treatment if it's there. Now, in the randomized block design setup, your total sum of squares is your treatment sum of squares plus the block sum of squares plus your error. All right, so that SSB sum of squares, we've basically pulled that away from the error. We're accounting for it separately. That's going to reduce the SSE. It's not going to affect the treatment sum of squares, but it's going to reduce the error sum of squares, and that's going to make the treatment relatively easier to see, relatively more significant. We also have two-factor factorial experiments. Okay, so this is a much more complicated design that we'll look at. Now, our total sum of squares, we're breaking it into two pieces that we're interested in. So here would be two treatments of interest. We have one of them will be called alpha, the other is beta. And we have two pieces that are going on for alpha and beta. There's what we call the main effect, and there's also an interaction effect. So that's the effect due to alpha and beta combined, and then your error. All right, so our sum of squares total breaks down into the sum of squares due to the alpha, the sum of squares due to the beta, the sum of squares due to the interaction between the two, and the error sum of squares. Let's look at an example of a two-way with interaction, an example ANOVA table of the two-way with the interaction so you can see what it looks like. So we're going to suppose we have two treatment effects, A and B, and there's an interaction between A and B. If we suppose that the A treatment effect has little a levels, the B treatment effect has little b levels, N is the sample size of each treatment, and capital N, so we're assuming that each treatment has the same number in there, although that's not necessarily a requirement. Okay, if N is the sample size of each treatment, then capital N equals little a times little b times little n is the total sample size. Your basic two-way ANOVA table then with the interaction term is this below. So here's your source. You have A, B, A times B, that's the interaction, your error, and then the last row is the total. Okay. Your sum of squares, your total sum of squares is going to equal the A sum of squares plus the B sum of squares plus the interaction sum of squares plus your error. The degrees of freedom, all right, we had little a levels of source A, so A minus 1 degrees of freedom there, B minus 1 for B, A minus 1 times B minus 1 for the interaction. All right, that's going to be the number of interactions, degrees of freedom we have, and capital N minus A times B. You can check that all of these add up to N minus 1 for the total degrees of freedom. Mean sum of squares, again, that's just the sum of squares divided by degrees of freedom in each case. And now we're going to have not one, as we did before, when we just had the one way with one treatment and then error, but now we have an F statistic for every variation source that we're modeling divided by the mean sum of squares due to error. Okay, so your A line, okay, which is looking at the significance of treatment A, is the mean sum of squares of A divided by the error sum of squares. Your B line is looking at the significance of treatment B. That's the mean sum of squares due to the B treatment divided by the error. There's your interaction line. Again, so each F statistic is whatever source we're looking at divided by the error mean sum of squares. All right. And the error mean sum of squares never has its own F statistic, right? Because we're comparing all of these to error. At the end of the day, the underlying question is your variation due to treatment A significant enough or large enough compared to the error variation, right? So in each case, we're comparing it to the error variation. Okay, and I'll wrap everything up. Linear model here is a flexible approach that's incorporating two major applications, okay? Regression and ANOVA. I've tried to stress that the underlying assumptions and really the underlying model are the same for each application. Both assume a linear structure, both assume independent, normally distributed errors, but the goals are different. For regression, the goal is build a predictive model. For ANOVA, the goal is determine which factors in the model are significant and which aren't. Okay. With regression, so we've pretty much the ANOVA table is pretty much, that's it. That is the ANOVA process. You get the output. Is it significant? Yes or no. Check the box, move on. With the regression model, there was more that we had to do, right? We had to go back and validate that our assumptions about the errors were correct. We have to compare we have to look at our average error to say, is it large enough? Or is the model predicting the variation in the model's predictions small enough for it to be useful? All right. So those are all things that we're doing that are important for a predictive model that we're not doing when we're just looking for significant factors. Is this variable in our model significant or not? Okay, that's not the same thing as saying, is this a good model and can I use this model to predict future behavior? Okay, so that's the end of the regression and the analysis of variance intro. Let's see. I'm gonna go ahead and pause here for a second and switch to something else. All right, to kind of wrap everything up on the regression discussion. There's one other presentation that I posted. There's nothing new in this presentation. So this is the one called the labeled Introduction to Regression and Correlation. If I'm sharing my screen, I should be able to see everything here. I'm going to open it up real quick. I'm not going to go all the way through it. This shows you much of the same stuff that was in the linear model presentation, but this goes into a little more detail on that example. Okay, so there's a little more detail in here. I recommend kind of going through and this kind of bit by bit, just to kind of fill in any blanks you might have. I do want to make a couple of points because we didn't really stress this before. Kind of one of the key starting pieces. We've sort of kicked off the regression discussion with, okay, we're going to build a regression model and this is how we would do it. But the first thing you would do, if you're given a data set like this and you're looking at it, is the first thing you want to do is before you go building a regression model is kind of determine whether there's really any point to doing so. And as with a lot of other things, a graphical tool can kind of go a long way to answering that question for you. So I'm gonna open up this this presentation. I'm sharing it here, but through Canvas, but it's kind of squeezing it funny. So let me open up in PowerPoint here. You should still be able to see my screen. So the very first thing before you go building a regression model is to kind of determine, all right, is there any point to doing that? Do you want to be doing that? The very first thing that you often do when you're looking at a response variable with a set of predictors is a scatter plot. Okay, it's a simple tool. We plot just a y versus x plot. A scatter plot or a scatter diagram is one tool that kind of will help show the relationship between two variables. You can follow that up with the correlation analysis. That's find the correlation coefficient, and that will tell you the strength of the linear relationship between those two variables. And it's note that that's only the correlation, though. We've kind of said this before. Causal effect is not implied, not answered by correlation. It's only really concerned with the strength of the linear relationship, not the relationship itself. But let's look at some scatter plot examples here. A scatter plot example, this is between a y and an x, can tell you, is the linear model what you should be looking at, or is there something else going on? So we have linear relationships on the left. On the right, we have curvilinear relationships. All right, and depending on if we're after a regression model, on the left here, this kind of tells us we need to be looking at the linear model that we were talking about before. On the right here, it tells us we need to be looking at a more complicated model. We haven't talked about those complicated models yet, but we'll get to that. Okay. It'll also, scatter plots will also tell you whether you have, strong relationships or weak relationships. Examples of the strong relationships are on the left, weaker relationships on the right. And here's an example where you might have no relationship between these two variables. Now, a word of warning. A scatter plot is a two-dimensional plot, okay? It's 1x, and in linear or nonlinear regression, you often have one response that you're interested in. There is a setting with multiple responses, but that's way beyond the scope of this class, so we won't get there. We're only interested in one response variable with one or more predictors. So a word of caution about scatter plots: it's not unheard of to have a case where there's no strong relationship between the y and any one of the x's, but that doesn't mean that there isn't a relationship between the y and the combination of the x's. Okay, so why scatter plots can be revealing as to what kind of relationship is going on, and if you're plotting a y with one of the predictors and you get something like this example with a strong linear relationship, that tells you, yeah, you really do have a linear model, right? If, on the other hand, you get stuff that looks more like this here, or even stuff that looks like you may not have any relationship at all, one by one, that doesn't mean that there's necessarily no relationship between the y and all of the x's together, right? So we will next time talk about multiple regression. We'll do a little bit more at the analysis of variance, but we'll talk about and go through a multiple regression example so we can see how it works, and we can see kind of compare it to the simple linear regression case. So okay, so that's kind of it for regression. I encourage you to kind of go through this example. In this case, this presentation, we had the home price example before. This presentation has tree trunk versus tree height data. Okay, so it's a slightly different example, but you're going to see it's you're getting all the same type of output, and it's walking you through all the same tests. All right, so it should be it's a good thing to kind of go through to sort of help. Again, provide like another example to compare what we had before. And the house price example is in here also, in addition to the tree example. So, okay. I think I'm just kind of flipping through, make sure there's nothing else that we need to focus on. And I do not think there is here. So with that, I think that pretty much wraps up our regression discussion and the ANOVA discussion. And so for next time, we'll go through an example of a multiple linear regression. So that's a single response and multiple predictors, and we'll look at how that works. It is fundamentally no different. And actually, you have all the same pieces. The math is really no different, and more importantly, from our standpoint, the output is fundamentally no different. There's just more of it. So, and there's some more questions that you answer as kind of part of determining whether you have a good model. But we'll get to that next time. Okay, I'm going to go ahead and call it there. Thanks, and I will see you next Monday. Again, just kind of refresh your memory. We will not have class tomorrow. So this recording will kind of serve as our lecture for tomorrow. And if you haven't seen the previous recording that I did, the audio recording, please check that out. And make sure you do that by next time. So, all right, thanks. Have a good night, everybody.